A while ago, I made a video about some research problems, open problems in mathematics. And the second problem that was on the list was about the universal convex body. And this problem was proposed to me in one of my geometry classes that I'm taking right now. And that instructor, I asked him where, he came up with this problem because he just kind of mentioned it as a matter of fact. And he told me that there is a book that discusses a bunch of problems in math, and it showed up in there. And I asked him if he could lend me that book, and he did. So I want to show you the book where that problem came from. It's called Unsolved Problems in Geometry by Hallard Croft, Kenneth Falconer, and Richard Guy. Falconer is a name that I've heard of before. I believe I used a book on fractal geometry when I was writing my thesis that was written by Falconer, so I'm familiar with him at least. And this book is not very big, as you can see, but it's just a collection of problems that supposedly are still unsolved. And I'm not sure how many of these have been solved or when this book came out exactly, but I thought I would show it to you and where the exact problem came from and how it was stated. The universal convex body problem. Okay, so here's the contents. We have notation and definitions, and then it's grouped in different sections. So section A is about convexity. You can see all of the different questions here that are supposedly still unanswered, like A11, for example. What can you tell about a convex body from its sections? Obviously, you have to read the problem to get a full understanding of it. Dido's problem. I always think of the singer Dido. When I open up this page and look at the problems, I see Dido jump out at me. Let's see here. Polygons, polyhedra, and polytopes. Tiling and dissection. I might actually look at some of these problems and try and take a stab at them. Packing and covering. I'm not entirely sure how hard these problems are, to be honest. I imagine they're pretty difficult if they're unsolved. Combinatorial geometry, finite set of points, general geometric. I guess this is the catch-all term, right? When it didn't fit into anywhere else, they just put it here, maybe. Euclidean Ramsey problems. I wonder what that's about. Magic numbers. Anyway, I thought I'd show you some of these problems, I guess. But let's start with the one that I proposed the other day in that video. Let's see, I believe it's here somewhere. I believe it's convex sets with universal sections, page 45. What number are we on? Yep, this is it. I recognize it. So what does it say? Does there exist a compact convex set K in R3 such that every closed plane convex subset of the unit disk is congruent to some plane section of K? The question, due to Ril-Narzutsky, is not as far-fetched as it seems at first, since there exists... Okay, so he did tell me this part, which was interesting. There does exist a four-dimensional K with this property. So what they're saying is that you have... So the question is about three-dimensional shapes, right? You want this three-dimensional shape such that whenever you slice it in any way, you can get any two-dimensional convex set. So there's a way I can slice it to get a square. There's a way I can slice it to get a circle. There's a way I can slice it to get like a teardrop shape. Whatever convex, 2D convex shape you can think of, you can slice the universal convex body in a way such that you get something that looks like it. That's what the question is about. But it says here that there exists a four-dimensional convex shape that has that property. So I might end up reading that paper or wherever that results from, because I want to see how he did it. It seems maybe there's something there that you can reduce to the R3 case. Let's see. Grunbaum showed that no centrosymmetric body K, so centrosymmetric, I believe, means that it's centered at the origin and it's symmetric about the origin in some way. I think the way that my instructor would say it is that K is equal to negative K, so you flip the points. flip the signs of the points. So no centrosymmetric body K can have a central plane section affinely equivalent to each proper centrosymmetric plane convex set. This was not possible for any finite dimensional centrosymmetric K. Okay, this will take a while for me to digest because I'm not entirely sure. I have to split this up to figure out exactly. I don't understand the problem very well, is what I'm trying to say. But here are some references if you want to look it up, if you're that interested in it. I think this guy, I'm not even going to try to pronounce his name, but he has a paper about universal convex set in Euclidean space. That might be a good place to start. There's other references up here too. Malden problem 41. And then I was just looking through this a little bit, and this just the problem right after it seemed pretty interesting to me. Convex space filling curves. In 1890, Peano published his construction for a space filling curve. Two guys asked whether such curves could be found so that all subcurves formed convex sets. In other words, we seek a continuous function such that for every a and b, a smaller than b in the unit interval, the image of f under that interval is a plane convex set of positive area. See, this is the type of result that just seems too good to be true. But I read that and I was like, it's short too. Look how short it is. And there's like 1 or 2 references on it. One is from Peano himself. I don't know. Some of these problems are interesting. I need to read more of them. But let's look at something else that's unrelated to convexity. Like, I want to see the tiling and dissection stuff. So let's see what here. Conway's fried potato problem. Okay, that already has captivated my attention. It's the first one on here. Tilings with a constant number of neighbors. Which polygons tile the plane? I think I saw a number file video on that. It sounds familiar. Decomposing reptiles. C17 reptiles. That's interesting. Okay, I'm going to show... Let's do the fried potato problem and then the reptiles one. So page 80 and page 99. That should be easy to remember. Page 80. Page 80, Conway's fried potato problem. In order to fry it as expeditiously as possible, Conway wishes to slice a given convex potato into n pieces by n-1 successive plane cuts, so as to minimize the greatest in radius of the pieces, which we denote by r. So if n is 2, the potato is a regular tetrahedron of edge length 1. Then there are at least 3 obvious ways to which to slice it. And then here he lists the ways to slice it. So A and B are about 12% and 5% worse than C. Is C the best way to do it? In general, does the best way always involve n-1 slices between planes of support which define the minimum width of the potato? Huh. So here he's got some pictures. 3 ways to slice a tetrahedron. So which way is the best way to cut a pyramid? The problems become even more complicated if the pieces can be rearranged at each stage before a plane cuts through them all, yielding as many as 2 to the n slices. Squared rectangles due to moron? What an unfortunate name. Imagine being a mathematician and your last name is Moron. Huh. He's got 1 reference. See, these geometry problems, I don't really know. Sometimes I don't even know how to start with them. This is why I've been on the search for a good geometry book. Let's do whatever 99 was. Reptiles. What's a reptile? An n-reptile is a two-dimensional region that can be tiled by n-congruent tiles, each similar to the whole region. We look for reptiles. Oh, I know what he's talking. That's like the dragon curve. Okay. We look for reptiles with a reasonably simple topological structure. Bounded tiles that are the closure of their interior. Any such reptile may be used to tile the plane by repeated subdivision and rescaling. Replication process is what gives them their name. So you can see that mathematicians like to get cute with their notation sometimes. To begin with, we seek reptiles that are convex polygons. The only such two reptiles are parallelograms. More generally, a parallelogram with side ratio 1 to square root n is an n-reptile. The body of theory on monohedral tilings of the plane should make a complete classification of convex polygonal reptiles possible. Such a reptile cannot have more than 6 sides. Analysis of non-convex polygons that are n-reptiles may be rather harder. Some examples are shown. All right, let's see some pictures. Let's see how a reptile leads to a tiling of the plane. So it's kind of like self-similarity, right? So you have this shape, and then we scale it down and build up from there. So you can see that this piece looks like this piece looks like that. So it's got 1, 2, 3, 4 pieces like that. But then, you know, it breaks down even further than that because inside each of them is another shape that looks just like this. Convex 2 reptiles. Are there any 2 reptiles other than the convex ones with reasonably simple boundaries? Okay, so what does he mean by reasonably simple? Fractiles. John Conway asked if there are any reptiles with holes, not simply connected. Grunbaum gave the example of figure C17. What's C17? Oh. Which is a 36 reptile, suggests that the proper question to ask is whether there is a connected open set whose closure is a reptile that is not simply connected. What is the least n for which this n reptile with any sort of hole? Wait, what? What is the least n for which there is an n reptile with any sort of hole? Oh, look at that, the Cantor set. Self-similar fractals give rise to reptiles with empty interiors, and these have been studied intensively. The simplest example is the middle third Cantor set. And he's got a bunch of references here if you want to look it up. I hold my camera steady. So you can see there's a lot of interesting... the geometry problems I find more interesting than normal. But, you know, that's just me. I like being able to see the thing that I'm studying. Sometimes in mathematics, it's almost impossible to draw the thing that you want to study. I think in algebra, well, it depends on what type of algebra you're looking at, but geometry is like the most tactile, if you want to say, of the mathematics, or at least in my experience, that is. But what do I know? Index of authors cited. Okay, anyway, I'll hold this page up here in case you want to pause and read some of the problems and then maybe Google it yourself. But I think that's good enough for this video. I'm going to look at some of these problems and see if I can take a stab at them. Again, he just let me borrow this book, so I got to give it back to him. So if I want to get some good problems and study them, get some references, I should do that ASAP. Anyway, this is a rather somewhat short video. I hope you found it informative. Let me know if you're going to pick this book up and read some of the problems, because it does look like a pretty interesting read. Thank you.